Good day. I'm going to do a little screencast here for you on the topic of differentiability implies continuity. In calculus, we study properties of functions. Before calculus, you study basic ideas of functions, basic mechanics of functions. You know, a function is a rule that takes for every input and assigns it to a unique output, right? That's a basic thing about functions. Another basic thing about functions are the types of functions that are out there, like polynomials and rational functions and exponentials and logarithms. In calculus, we're going to study some general properties of functions. One of those properties that we've studied is continuity. Okay, so if we have a function, f of x, x is its independent variable, y is its dependent variable, and if we have some input, x equals c, we can say the function f of x is continuous at an input x equals c if the following is true. If the limit as x goes to c of f of x equals f of c. This is the definition of what it means for a function to be continuous at a point. It's important that we all know this. This is something you should know and you should be able to talk about and work with in problems. But you also should know, almost as important, or almost equally important, is what this means. So it's got a geometric interpretation. And when I say geometric, I mean the graphical. Maybe let's just say that. It's got a graphical. It means that if I have an input of a function, that saying that this limit exists means that as my x's go up to get closer and closer to c from below, my function values are going to approach some value. And then if I look at x values and they get closer and closer to c from above, my function values are going to approach the same value as they did from the other side. That's what it means for a limit to exist. And what continuity says is that the value they're approaching is going to be the value of the function. And so the value of the function is right there. There's no hole. Okay, the limit exists and there's no hole. So this is what it means to be continuous at a point. And then what does it mean for a function to be continuous on an interval? A function's continuous on an interval if it's continuous at every point of the interval. Well, what does that mean? It means you can graph it without taking your pencil off the paper. That's continuity. Okay? And it's defined in terms of this property that uses limits. Differentiability is another property. Okay, if you have a function y equals f of x, and you have an input c, we can talk about what it means for a function to be differentiable at c. So the formula for that is this. It's differentiable at c if this number we call f prime of c exists, and f prime of c is defined to be this limit. Okay, so a function's differentiable at a point if this limit exists. Well, so that's the definition. You got to know it. It's really important. There's no getting around it. Okay, you got to know this to feel like you've learned calculus. But what does it mean? So let's connect it to your gut. Well, what does it mean? Well, if you look at this thing here, this quotient, we call it the difference quotient. It is a formula for the slope of a secant line. And then when you take the limits of the slopes of the secant line, okay, so you throw this sucker in, then this whole thing is the slope of your tangent line. So when we talk about differentiability, we're saying this number here, f prime of c, exists. But what does that mean? It means the tangent line exists. That is, the graph has a property that you can draw a tangent line to the graph at that point. So graphically, so I'll write that here, the graphical interpretation is that if you've got a function, you got your input here, you've got the point at x equals c. Well, if it's differentiable, it means you can draw a tangent line. There is a tangent line there. There's a unique tangent line that has a unique slope, right? And we're interested in that slope because that's what this value is. Okay? So what you learn about the calculus is that if the tangent line exists, that tells you something about the function at that point and around that point, actually. And that's what I'm going to prove to you today. That's the theme of the screencast. Differentiability implies continuity. So I'm going to state a theorem, the basis of mathematical knowledge. The basic building block of mathematical knowledge is theorems. It's theorem 3.1 in our textbook, and it's on page 237. All right. So I'll tell you the anatomy of the theorem after I write it. So let f of x be a function and let x equals a be a point in the domain of f. Okay. Then the theorem says if f of x is differentiable at x equals a, then f of x is continuous at x equal a. Okay, so this is what this is a fact, a mathematical fact, and I'm going to prove it to you mathematically. So there's two things I want to do next. So one thing I want to do is show you something about the anatomy of this theorem. And the second thing I'm going to do is show you an alternate way to define the derivative. It's come up in the book already, so hopefully you've seen it, but I'm going to just show you this other way. So, but first, the anatomy. So theorems have two things in them you always need to know. One is the hypothesis, or the assumptions, or sometimes they're called the givens. Okay. And the other thing they have in them are the conclusions. Okay. So let me show you in this theorem what the hypotheses, assumptions, or givens are. Okay, so one of the givens is f of x is a function. Okay. Shouldn't be a surprise because of the notation. The next thing that's given is x is a point in the domain of the function. And then the other thing that's given is that the function is differentiable at x equals a. So you can treat these as facts. You know that these are true. And you can use those truths and logic to deduce other things. So the conclusion in this theorem is that f of x is continuous at x equals a. And so in a proof, you want to make logical deductions from the givens that allow you to arrive through logic at the conclusion. Okay? And logic are statements like, if something is true, then something else is true. So if you know something is true, then you can say something else is true. That's a logical deduction. So you'll see how I do this. So that's number one, the anatomy. Now, number two, I'm going to show you an alternate way to define the derivative. So here's an alternate definition. So if I've got y equals f of x, and I've got x equals a is a point in the domain, I can define the derivative as follows. The limit as x goes to a of f of x minus f of a over x minus a, that is f prime of a. So this is a slightly different version of the derivative than we've seen before. We're comfortable with this next definition. The limit as h goes to 0 of f of x plus h minus f of x. Oh, these should be f of a plus h. So f of a plus h minus f of a all over h. That's f prime of a. Okay, so what I want to show you is why this and this are the same thing. So if you look at the two, look at the denominator of the difference quotient. Okay? And suppose x minus a is the same thing as h. So let's take that as a given. Okay, and everything else is going to flow from that. Then, well, I can add a to both sides here. Then I get x equals a plus h. All right. So then, look what I just did. There's an x here, and there's an a plus h here. So I'm saying if this x minus a and that h are the same, then I just showed that this x and this a plus h are the same. And then that means here in our difference quotient, this is clearly the same as that. So I've just shown that these difference quotients are the same expression, right? You should believe that these difference quotients are the same thing. Okay, so now the question is, how do we go from here to here? Okay. Well, let's come back and look at this. Okay. X going to a means x gets closer and closer to a. Okay. If I subtract h from both sides, or rather a from both sides, that means x minus a is getting closer and closer to a minus a, but a minus a is 0. So if x gets closer and closer to a, then x minus a is getting closer and closer to 0. But what is x minus a? That's what I was calling h. Okay? So I've just shown that if x is getting closer and closer to a, in this relationship, that means h must be getting closer and closer to 0. So that's why these two different definitions are the same. They're the same just by a manipulation of symbols. Okay? So in the proof of Theorem 3.1, I'm going to use this alternate definition for the derivative. Okay? That is to say, I'm going to use the fact that f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a. Okay? So let's swipe back here a second. And let's copy this theorem. I'm going to put this right here. So this is what I want to prove. So here's how the proof is going to go. I'm going to say we know f of x is differentiable at x equals a. Okay, and what that means is f prime of a exists, and it's the limit as x goes to a of f of x minus f of a over x minus a. Okay, so this limit exists and equals this number here. So now what I like to do when I write a proof is to write down what we want to show. We want to show that the limit as x goes to a of f of x equals f of a. That's what it means for a function to be continuous at x equals a. That's the conclusion that it's underlined in red above. Okay. So when we're proving things, I want to prove this. So I'm going to start with the left-hand side here. So I'm going to say, consider that, all right, the limit as x goes to a of f of x. Now watch this. It's the same thing as the limit as x goes to a of f of x minus f of a plus f of a. Okay? So you see what I did there? I just added and subtracted a number. So they cancel out. That's really just 0. So these two statements on either side of the equality are the same. Okay? So now what I'm going to do is this. Before I turn the page, I'm going to group this. So f of x minus f of a plus f of a. So I'm going to group that, and I'm going to work with it that way. And notice the first grouping, that f of x minus f of a, if you look at what we know right here about the fact that our function is differentiable at a, f of x minus f of a appears in that numerator. So by grouping this thing in this way, I'm putting myself in a position where I can maybe start taking advantage of that numerator. But what I'm going to need is I'm going to need that denominator, that x minus a in the denominator. Okay, so let's take this and copy it so we can start it on the next page. All right. So now what I'm going to do is another great algebraic trick. I'm going to multiply that thing in parentheses by the number 1, x minus, but written in a cool way, x minus a over x minus a. And the reason I'm going to do that is because I can use the properties of numbers to move that one of that x minus a's underneath the f of x minus f of a, and I'm going to leave the other one outside. Okay. So with that done, you'll see this thing right here is the difference quotient in the limit definition of my derivative, the new one I gave you. So now I'm going to use properties of limits to calculate this limit up here. So I'm going to use the limit of the product as the product of the limits. And then here, I gotta put this in here too. Okay, so what does this mean? Well, this means, let's do the easy one first. This here, I'm taking the limit of a constant, so that's just equal to f of a. So I'll write that in last here, f of a. That's easy enough. Now let's look at this. This is the derivative of f prime of a, the definition of the derivative. So I can write that as f prime of a. And then just let me leave this here for a second. Okay. Now, I can write that there, f prime of a, because we assumed, as one of our givens, that the function's differentiable at x equals a. This was the definition of what it means to be differentiable, so I could just substitute that for this, the f prime of a. And that's just a number, right? And this is just a number. Now, notice what's happening here with this limit. the thing I'm taking the limit of here is just a polynomial in x, right? So it's continuous, so I can evaluate the limit by just plugging in a. And so I get f prime of a equals a minus a, or not equals, f prime of a times a minus a plus f of a. But a minus a is just 0, and so I'm left with f of a. So if you trace these equalities back, you'll see I've just shown that the limit as x goes to a of f of x equals f of a. And that's what I was trying to prove. If a function's differentiable, then it's continuous. That's the end. Let me know if you got questions. Ask in class, ask in the discussion forum on Canvas, ask during student hours, or just shoot me an email or a text. See you in class.